Some of the coolest things are super. Superheroes, supercars, Super Smash Brothers. There's something super in the materials world too, and while it's not quite as well known, I would argue it's just as cool. This is the story of nickel superalloys. There are a lot of alloys out there, but what makes something a superalloy? In general, a superalloy is simply a metallic alloy that's designed for high temperature, high stress applications. While that might seem a bit vague and not all that interesting, the truth is that the highest performance superalloys are truly unique and special materials. There are several fundamental properties that make them unlike any of the known superalloys you encounter in everyday life, and that ability to withstand high temperatures is more important than you might think. More on that later. Superalloys require a special design because metals generally lose a lot of strength at high temperatures. A common alloy like steel won't actually melt until about 1400 degrees Celsius, but it loses pretty much all of its strength well before that. There's a phenomenon called creep that describes the behavior of these metals at high temperatures. There are many kinds of creep, but the ones that dominate at higher temperatures are generally diffusion dependent. Basically, atoms tend to move around a lot more at high temperatures. This applies to both diffusion of individual atoms in the lattice into neighboring sites, and the movement of crystal defects called dislocations. Therefore, to make a metal suitable for ultra-high temperature applications, we need to suppress diffusion and dislocation movement. Now that we know the challenges, we can start to go over some of the strategies used to make an alloy that's able to operate at extremely high temperatures. First of all, why nickel? Well, superalloys in general can be based on iron, cobalt, or nickel. But nickel is typically the primary element in superalloys that operate at the highest temperatures. Part of the reason is that nickel retains the same structure all the way from room temperature to its melting point, namely face-centered cubic. Iron and cobalt both undergo phase transitions along the way. Next, we have to understand what happens when we start to alloy nickel. Let's use aluminum as our alloying element. If there's only a bit of aluminum in the system, the aluminum atoms can substitute anywhere in the lattice. There's no real order or structure to their arrangement. This is called a solid solution, and it typically only exists when the concentration of the alloying element is very low. In superalloys, this phase is called gamma. If we keep adding aluminum to the system, eventually this solid solution becomes unstable. It becomes thermodynamically favorable for the aluminum to arrange itself in an ordered structure, where it will only occupy certain sites. This phase is called gamma prime. At first, this might seem like a pretty minor difference. The basic shape and structure of these two phases is almost identical, and both are composed of nickel of aluminum, but their properties are quite different. When metal atoms form ordered structures like this, it's called an intermetallic. Since this structure wants to retain this ordered arrangement, dislocation movement and atomic diffusion are generally suppressed. To give a simplified example, let's imagine a vacancy in the gamma phase. Here, regardless of where the vacancy is, it's pretty easy for any of the closest adjacent atoms to move into it. There are no preferred sites for nickel or aluminum, so this sort of diffusion is relatively easy. On the other hand, if we try the same thing in gamma prime, the mechanism isn't quite as simple. If there's a vacancy in an aluminum site, the nearest atom is nickel, and it doesn't really want to jump in here. Remember, the thermodynamics favor an ordered structure. This site wants to be aluminum. In reality, it is possible for nickel to occupy this site, making what's known as an anti-site defect, but the energy barrier to do so is higher than in the gamma phase. The same principle applies to dislocation movement, although it's a little harder to visualize and somewhat coincidentally involves the concept of a super dislocation. The fundamental idea is the same though. Since this is an ordered phase, the atoms can't move around amongst the structure as easily as they can in the disordered gamma phase. As a result, this gamma prime phase seems at first glance to be flat out better than the gamma phase. We started out wanting to suppress dislocation movement and atomic diffusion, and we can do both by turning our gamma into gamma prime. But there's one big problem with this sort of phase. You see, dislocation movement is what makes metals ductile at low temperatures, and with no dislocation movement in the gamma prime phase, it's rather brittle. Even though this is still a metal, in terms of mechanical properties, it's almost like a ceramic or glass material at room temperature. In other words, it's very hard, but one crack or sharp impact can mean catastrophic failure since it can't deform like a typical metal. This is a big reason why most metals you see in structural applications are primarily one element. If the concentration of the alloying element is too high, often these intermetallic phases form, and the lack of ductility makes them unsuitable for most mechanical applications. So, we can't make our entire alloy out of the intermetallic gamma prime phase, but it's still quite useful. You see, if we have the gamma phase with gamma prime inside of it, some good things start to happen. The gamma prime phase helps by blocking dislocations and slowing down diffusion at the boundary with gamma, resulting in stronger high-temperature material. Now, this concept isn't necessarily unique. There are many other alloys that have a hard intermetallic phase within a solid solution, but in superalloys the amount of the intermetallic phase is remarkable. In terms of volume fraction, around 70% of the material is made up of this phase. What's amazing is that despite the high percentage, gamma is still the continuous phase. Because of how the solidification kinetics work, a structure is made that is basically gamma prime blocks within a gamma network. Every point of gamma is connected. It's basically like the mortar between bricks, just bricks small enough to fit across the end of your hair several hundred times over. The preservation of this continuous gamma prime phase is critically important because it allows a superalloy to maintain some low-temperature ductility despite being made out of the mostly brittle gamma prime phase. If any point along this path were entirely gamma prime, that wouldn't be the case. In addition to the unique alloying strategy, nickel superalloys have one more fundamental difference that makes them good at handling ultra-high temperatures. You see, in most metals there are many different crystal orientations within the material, called grains. This makes perfect sense if you consider a molten metal that's starting to solidify. Crystals will start to grow at various points in the molten metal as it cools, but there's no preferential direction. Inevitably, when the material finally solidifies, the material will be a patchwork of grains with different crystal orientations. This usually isn't a bad thing. Odds are that every metal you've ever seen or touched is this sort of polycrystalline arrangement. In fact, grain boundaries can even strengthen certain alloys by providing a barrier against dislocation movement. But there's a problem for high-temperature applications. Diffusion is very fast along these grain boundaries, and at high temperature these grains can actually start to slide along the boundaries. For this reason, nickel superalloys designed to withstand the highest temperatures are a single crystal. This can be done by passing the molten metal through a grain selector as it is being slowly solidified. At the start of this spiral selector, the crystal has many orientations just like a typical metal, but the crystals aligned in a particular direction grow the fastest, making misaligned crystals eliminated in the bins. By the end of the grain selector, there's only one crystal direction left. This is the reason why you'll sometimes see a pigtail-looking shape at the end of freshly made superalloys. The unique phase structure and single crystal nature are two of the most interesting and unique features of superalloys, but the truth is that we've only scratched the surface of superalloy theory and design. Other alloying elements like molybdenum, chromium, cobalt, and iron are often added to strengthen the gamma phase, while titanium, niobium, tantalum, and vanadium can further strengthen gamma prime. The latest generation of superalloys even have metals like rhenium and ruthenium added for increased high-temperature strength and stability. These are two precious metals rarer than gold. It's an unbelievably complex system, and to this day millions of dollars are put into research and development to further refine and optimize these alloys. So, at this point you might be wondering why. Why so much time, effort, and money spent developing these things? What's the point of a metal that can withstand slightly higher temperatures? Well, superalloys have a few applications, but for the state-of-the-art single crystal materials that we've just discussed, there's one particularly important one: turbine blades. Obviously, the inside of something like a jet engine is extremely hot, and believe it or not, we'd like it to be even hotter. You see, any combustion engine like this is governed by the Brayton cycle. I won't go over all the math here, but the end result is that the greater the temperature difference between the combustion and the outside reservoir, the greater the maximum efficiency of the engine. To maximize the safe temperature that turbines can operate, modern jet engines and gas turbine blades use a single crystal superalloy with cooling channels running through it and a ceramic coating like yttria stabilized zirconia. The development of superalloys, along with advances in cooling and thermal barrier technologies, has allowed the maximum temperature of jet engines to increase significantly over the last 30 years. The result is that the latest superalloys can withstand prolonged exposure to temperatures in excess of 1100 degrees Celsius. Because of the thermal barrier coating and cooling channels, the actual maximum temperature inside the turbine is even hotter. Considering the amount of jet fuel used every year, it's likely that the development of these materials has saved literally millions of liters of fuel. The economic and environmental impact of the fuel savings is truly staggering. So, that's part of why these extraordinary alloys are truly worthy of being called super. They don't stop a giant alien invasion from destroying Earth, but they're helping to save our planet in a different way. And while listening to me ramble on about the material science behind an obscure metal might not make for the same compelling viewing experience as the latest superhero movie, I hope you find the story of nickel superalloys just as amazing.